Hello, and welcome to the lecture on Chapter 14 from Astronomy Today, 8th edition. In this chapter, we're going to talk about solar system debris, which is basically everything about the solar system that we have not talked about yet. This concludes our mini chapter survey of the solar system. We talked about each of the planets, starting with the terrestrial planets closest to the sun and working our way out. Now, as I said, we're going to cover everything else. So we're actually going to go back towards the sun a little bit to talk about the asteroid belt, because we last talked about Uranus and Neptune on the edges of the solar system. But then we'll return to the very edge of the solar system, where we'll talk about the Kuiper belt and Kuiper belt objects like Pluto, and then finally we'll talk about the Oort cloud as well. So let's take a look at this chapter, at the contents. So we want to talk about asteroids and comets. We definitely want to be able to distinguish between the two, okay? Then we want to talk about an important aspect of collisions of asteroids with planets in the context of what killed the dinosaurs about 250 million years ago. We'll then talk about Beyond Neptune. This is where we'll talk about the Kuiper belt and the Oort cloud. And we'll talk about the meteoroids. Those are the rocks that we find on Earth primarily. And those tell us a bit about the primordial solar system because they come in different shapes, different sizes, different chemical compositions. Okay? All right, so let's get on to this chapter. So we'll start out with asteroids. So asteroids are quite small. Most of them are just a few hundred meters across or thousands of meters or even smaller. They also mostly have eccentric orbits, and an eccentric orbit is not a perfect circle, so they have very elliptical orbits. All right, and they're in the asteroid belt, which exists between Mars and Jupiter. All right, so the asteroid belt is a stretch of the solar system. We can see it here with these scaled orbits, right? So all the orbits are to scale here. The planets are not to the same scale, but the planets are scaled to each other, right? So the relative sizes of Mars and Jupiter, for example. But here we can see the asteroid belt exists between the orbit of, of Mars and Jupiter, right? And we can look at a particular typical asteroid orbit right there, and then a specific asteroid orbit like the Amor asteroid, which just really highlights how eccentric they can be, because the Amor asteroid actually comes within Earth's orbit. We can see where it crosses, interior to the closer to the sun than Earth. All right, and here's another, the Apollo asteroid, also highly elliptical orbit, right? So highly eccentric. But the point being is that the typical, right, the average orbit occupies this band right around here. Okay. Furthermore, there's two special types of asteroids that aren't technically part of the asteroid belt, and those are the western and eastern Trojan asteroids, like the Trojan horse, because these are actually in Jupiter's orbit. Okay? And here is an example of the largest known, really not so much an example as just here is Ceres, the most famous and largest asteroid there is. In fact, it is the only asteroid that is qualified to be classified as a dwarf planet. Okay, there is no asteroid that is large enough to actually be considered a dwarf planet. A dwarf planet is the same classification that Pluto has. Okay, so asteroids are rocky. Remember that, because it's different from comets. There's over 600,000 that have been identified so far. All right, the big three, the largest ones in the asteroid belt, are Ceres, the actual planet-sized asteroid, or maybe large moon-sized asteroid. Pallas, also quite large, although noticeably different from Ceres. Ceres really stands alone. And then close to Pallas, we have Vesta. Now, Ceres is actually a sphere. Pallas and Vesta are not, which is important for them not being classified as dwarf planets. Pallas and Vesta are more potato shaped. They're large. There is significant microgravity. Nothing that would be comparable to a true world's gravity, but it would be noticeable. You'd accelerate towards the ground. But they're not large enough to have that spherical shape. Essentially, they're not large enough to compress the rock into a sphere. So Vesta, in terms of special asteroids, is unique because it shows evidence of volcanism. So we actually see that Vesta heated up enough, there was molten rock inside, and that molten rock rose to the surface and actually created these low gravity volcanoes. Okay, and there are three types, all right, of asteroids. There are C-type, which are carbonaceous. They're very dark, right? So think like, burnt, ashy coloration, because that'd be very carbonaceous. There is silicate, all right? So these are rocky silicate rocks. This is the same type of rock that is the most predominant type of rock in the crust of our own planet. So lots of silicate rocks here on Earth. There are some asteroids that also are primarily silicate. And then there's metallic, M-type asteroids. And those have a lot of iron and nickel, right? Iron and nickel is spread in small quantities in the crust of Earth. There's more iron and nickel deeper down, inaccessible beneath the crust of Earth. But the fact being is there's some asteroids that have huge amounts of iron and nickel. More iron and nickel on just one asteroid than have ever been mined here on Earth. Okay, so here are two small S-type, that's the silicate type asteroids, Gaspra and Ida. All right, they were visited by the Galileo probe, which is one of the few probes that has actually gone to an asteroid. All right, and here Gaspra is in false color. It is really quite gray. And then notice that Ida has its own moon, Dactyl. All right, so here is Dactyl, the moon of Ida. Now, is that totally rare? Is that unheard of for asteroids that have their own moon? No. There are quite a few of these, 50 so kilometer asteroids that have these tiny, just maybe 1 kilometer moons, because the same gravitational effects apply between asteroids, creating a stable orbit, okay? And so you can have this very, very tiny moon. Because the gravitational acceleration is so small, the orbital period of that moon isn't what we expect. Everything is essentially in slow motion, but it still is a moon. It's still orbiting Ida, all right? And moons, like Dactyl, are so important because based on that period of orbit and the easily measured semi-major axis of that orbit, we can calculate the mass of Ida. And since we can clearly calculate the volume of Ida by just looking at its shape, right, and doing lots of good calculations about its volume, then we can find its density. Once we know its density, well, that's really one of the ways that we can confirm the S-type. Because we say, okay, well, it's not dense enough to be iron or nickel, and it's certainly dense enough to be silicate. Okay. All right. Here is another mission to an asteroid. So the NEAR spacecraft visited this C-type asteroid, so a carbonation asteroid called Mathilda. All right, it's a mouthful, but Mathilda, on its way to its main target, which was Eros. And Mathilda, like many other asteroids, has a very low density, and it's probably not solid, right? So it's like full of like big air pockets, right? And it's at very, very low density, okay? And that is certainly the carbonaceous asteroids, those ashy asteroids, have the lowest density, okay? All right, Eros does seem to be solid, right? Here is another asteroid. So this is a rockier asteroid. Right, we can see lots of impact craters, and it's withstanding that force. Here you can really see there's not spherical shape. You can see the unusual shape of Eros. All right. The asteroid Vesta is thought to be a genuine protoplanet dating back to the formative stages of the solar system. Right, so Vesta is forming like Earth would have been forming around that same time, in the first couple hundred million years of the solar system, kind of right up to that period of bombardment, once the planets were big enough to be bombarded. But it just never was able to accrete enough matter to really get larger, and so it was left in that protoplanet stage. All right, but today we actually don't even quite classify it as a dwarf planet because it did remain so small that it does not have a true spherical shape. It's close. Vesta's very close to being spherical in shape, right? But it's just not quite there. It's just not large enough. There's not enough force of gravity to really shape the rock into a sphere. Okay, so some asteroids have orbits so eccentric, right, that's so elliptical that they cross Earth's orbit. We saw an example of that a few figures back. They are called Apollo asteroids and raise the concern of possible collision, right? So you have to pay attention to those asteroids when they come by and think about because if you think about the period of Earth's orbit and the period of asteroids, we keep passing past each other, but the relative distance when that asteroid passes within Earth's orbit isn't always going to be the same for each rotation of Earth or each orbit of Earth. And so there could be a time when they just happen to be in the same place at the same time, and then that's a collision course. All right. So there are 10,000 such asteroids that have been discovered so far, of which about 1,400 have been designated as potential hazards due to their size. Okay. So we track those. We make sure we can predict when their closest encounters are going to be. And there's none that are definitive, terrible collisions that we know of, and we're just tracking all the ones that are out there. Okay, here is the asteroid Totatis, imaged by the Chinese spacecraft Chang'e 2 or Chang'e 2. It is the largest of more than 250 potential hazardous asteroids that come within a 5% of an astronomical unit, right? So that's within 5% of our distance from the sun, of the Earth, between the years 2002 and 2000 or 2012. During this tracking period that your textbook is referring to. And this is ongoing work. I mean, it was in the news just recently that there was a close flyby. I think it was like Apophis or something, and that Apophis asteroid was very close by, and it's going to be even closer by in 20 years. And so we just have to make sure, because there's error in our calculations, there can be slight perturbations. We have to make sure we're right, and just keep checking on these asteroids. If there was going to be a collision, we try to find out where it was going to take place or if it could be avoided. All right. So now I mentioned, so far we've talked about the primary asteroid belt. We talked about those Apollo asteroids that come within Earth's orbit. Now we're going to refer back to that other classification of asteroid, those Trojan asteroids, okay? And they orbit in these special points, which are called Lagrange points. All right. Now, Lagrange points are balance points between gravitational tugs. Now, obviously, the sun runs the solar system. The sun's gravitational forces dominates the solar system. If you think about the gravitational acceleration caused on Earth due to the sun's pull, and compare that to the gravitational acceleration caused on Earth due to, say, Jupiter's pull, well, the sun is way bigger, right? Much, much bigger. Also, if we consider satellites in orbit around Earth. If we think about the gravitational pull on Earth satellites, or artificial satellites, like communication satellites, and you consider the gravitational pull on those satellites that puts them in a stable orbit, okay, that keeps them in a stable orbit. Well, doesn't the moon also pull on those satellites? Yes, right? You can consider the International Space Station. The International Space Station is pulled on by the moon, but that gravitational tug from the moon, tiny. However, if you get just the right location, where you're much closer to the smaller body, like say much closer to the moon than Earth, or much closer to Jupiter than the sun, then you can get a balance point where the gravitational tug from Jupiter, so the tug from Jupiter, so Fg for gravity, J for Jupiter, is equal to the gravitational tug from the sun, right? So there's an equilibrium, because there's some component of the gravitational tug from the sun in that direction. Now, primarily, obviously, the force is going to be in this direction, but there's going to be a component in this smaller direction, and then you can balance out those two components and create a Lagrange point, because that's what a Lagrange point is, right? A Lagrange point like L4, L5 are balance points. Okay, they're gravitational balance points. And then there are other ones as well. They're actually simpler to understand because they're on a straight line, like L1. L1, there's a gravitational pull towards Jupiter. There's a gravitational pull towards the sun. Those two forces cancel out, and you've got an equilibrium. You've got a balance point right there at L1. Okay, and honestly, mathematically speaking, L1, L2, these are Lagrange points 1 and 2, and Lagrange points 3 are the easiest to calculate. 4 and 5 take quite a bit more sophisticated mathematics, okay? But it's 4 and 5 that we care about because that's where the Trojans are located, all right? Now, it's not to say you can't locate things at L1, 2, 3, and 4. It's just that they're not as stable, and naturally occurring satellites don't show up so much in the Lagrange points 1, 2, and 3. And I talk about these labeled Lagrange points 1, 2, and 3 like that's a common thing, and it is, because every two-body system has Lagrange points. Of course, here we're comparing between Jupiter and the sun, but as I said before, there's Lagrange points between Earth and the moon. There's Lagrange points between Earth and the sun. Every two-body system has these balance points. We take advantage of those of artificial satellites. There's a famous, or very, very soon to be famous, space-based telescope, much like the Hubble telescope, but more sophisticated, called the Weber telescope. It's going to be placed in L2 between Earth and the moon. So we're actually going to place an artificial satellite at that balance point, so we'll stay there relative to the Earth-Moon system. Same idea here. Because if you put Trojan satellites, or Trojan asteroids, at L4 and L5, they stay there relative to Jupiter and the sun. So as Jupiter moves, they move with Jupiter. That's the idea of the Trojan, because they're sneaking up with Jupiter, because they're in the same orbit, but only in that particular location, right? Pretty neat idea. Okay, so now on to comets. Okay, so comets that come close enough to the sun to be detectable from Earth have very eccentric orbits. Very eccentric orbits. There are some comets that never come close enough to be detected. They stay in the outer solar system. They might have less eccentric orbits in that case, right? And just the sheer scale of their eccentric orbit puts the eccentric orbit of asteroids to shame, because we can have a major axis that's thousands of astronomical units. right? It's so much bigger than the orbits of even the distant gas giants like Saturn and Jupiter. And even if we were to include Neptune and Uranus, the comet would still go well outside of their orbits. Okay? So comets have a very small nucleus and a coma of gas, basically cool gas that's gravitationally held onto that nucleus, and dust, all right? That is the most visible part and can be very large. A hydrogen envelope, a dust tail, and an ion tail. Okay, so see that? They have an envelope of hydrogen gas, right? Cool hydrogen gas. They have a dust tail, so small particles made out of, carbon molecules, heavier elements, okay, everything you would expect, right? Definitely, the dust is not going to be the, it's not water ice, it's actual dust, actually heavier elements. And they have an ion tail, which is just basically ionized molecules, those that have lost electrons or gained excessive electrons. Okay, so we can see right here's an example of the tail of the comet. The tail always has multiple parts to it. We'll talk about those multiple parts to the tail. Here's the hydrogen envelope. Here is the coma, which is also gas, but denser gas than hydrogen. And there's the small, dense nucleus. The nucleus would be rocky. Okay? So the comet's tail always points away from the sun due to the solar wind. The ion tail is straighter than the dust tail. Okay? Why is that? Well, because the ion tail is being pushed by the charged particles of the solar wind. So it gets pushed directly in that direction. There is an electrostatic force acting on that tail. Okay? Because the solar wind, again, is charged particles, primarily electrons, that are being accelerated away from the sun, all right, or were initially accelerated and they're traveling away from the sun. Now the ion, on the other hand, the dust tail isn't ionized. Those particles are neutral, all right, they're ionically neutral, and so they're being pushed away from the sun, not by the solar wind, but actually being pushed by photon collisions. So photon collisions, because individual particles of light, known as photons, actually carry momentum, but it's a very small amount of momentum, thus it's smaller push. So that means that the inertia of the dust makes it so that that tail isn't pointing directly away from the sun. So for example, this is a wonderful example of that idea. We can see the ion tail pointing really directly away from the sun, and the dust tail having more of that being dominated by the inertia of the dust particles, but still being gradually pushed away from the sun. Okay? All right. So the comet's tail develops as it approaches the sun and disappears and moves away. So comets spend most of their time without tails because they're so hard frozen that there's no gas to create the tails. Right? All that gas returns to a solid state or a liquid state at the very least. Okay? So the ion tail always points away from the sun. The dust tail curves a bit as the comet gets ahead in its orbit. Okay? So you can see, right, that the dust tail, definitely has a shape that points away from the sun, but has that curve due to inertia. Okay, due to inertia, because this orbit here is shown as a counterclockwise orbit, which is typical of comets. Not exclusive. Comets can have both retrograde, which is clockwise, and counterclockwise orbits, because they can come from such distant parts of the solar system that they don't come with one particular predetermined direction, like all the planets, are orbiting in the counterclockwise direction. Not true of comets. Okay. So Halley's Comet is one of the most famous. It is a period of about 76 years and has been observed since antiquity, so it's been documented by humans for thousands of years. Its most recent visit was in 1986, all right, which was not spectacular, all right, because it wasn't as visible. The tail wasn't as dramatic. All right, the comet in 1910 as seen with the naked eye, and the comet in 1986 as seen through a telescope. Okay. So you can really see that there's just, I don't know if the Halley's Comet is just running out of material, or perhaps it just wasn't whatever process didn't allow it to create as large of a tail in the 86 pass by. So Halley's Comet has a shorter period than most, however, right? Because 86 years might seem like a long time, or 76 years, to wait for a comet to come back, right? But it's on the short end. There are some that come back much less frequently, all right? But its orbit is not in the plane of the solar system, probably due to an encounter with a larger object. Okay, so Halley's Comet, the orbit that it has now is not the orbit it would have had millions of years ago. Okay, so you can see here the highly tilted orbit of Halley's Comet, in terms of its plane of orbit, and then here we see the plane of the solar system, otherwise known as the ecliptic plane. All right. But that's not unheard of. Certainly there are other comets that have these highly tilted orbits. Okay, so the typical comet mass is between 1 trillion and 1,000 trillion kilograms. Each trip close to the sun removes some material. So Halley's Comet, for example, is expected to last about another 40,000 years, and it'll basically be just not have enough gas left to really be a comet. It'll just have burned itself up, evaporated essentially. And sometimes a comet's nucleus can disintegrate violently. Right? So sometimes there can be a process where there actually will be a sort of explosion, but a chemical release of energy from the nucleus. Okay? So what killed the dinosaurs? So far we've talked about asteroids and comets. Well, was it one of these? Yeah, it was probably an asteroid, right? Also possibly a comet, but absolutely. The time scale is about right, all right, in terms of the collision. Basically, that's in terms of the frequency of large collisions. It's the average frequency. It's certainly not unheard of for a collision to happen that frequently. So it has happened throughout Earth's history. If you look at the geological record, having it happen 250 million years ago, completely reasonable. Furthermore, evidence exists for an impact crater of the proper age, and there is an iridium deposit all around the world. So if we look at, say, like the polar ice caps, we can see at the same time that the dinosaurs went extinct, we can see this deposit of iridium dust. And iridium is very, very rare on Earth, but is common in certain types of asteroids. So that would have come from the vaporizing of the asteroid upon impact. All right. So did an asteroid cause the extinction of out of the blue accelerate ongoing extinction, or, well, we're not sure, right? Was there was there already climate change happening that was making it difficult for this dominant group of species to be on the planet? Yes, possibly, but it could have just been enough. There could have just been enough effects from that one collision to just create a series of chain events that led to the extinction of all the dinosaurs. All right. So a little bit more about comets. The Stardust mission flew through the tail of the comet Wild 2, gathering dust particles in its detectors made of aerogel, right? So very, very low density gel, and returning them to Earth for analysis, right? So we actually caught the particles in the gel, right? And the gel is so light that it was able to trap these individual particles, because these are tiny, tiny little particles, but they're actually embedded in there. So really great opportunity for scientists to discover, that what it took to stop these particles, because that can give you some idea of how energetic they were, and also then we actually have them for direct chemical analysis. Okay, there was also the Deep Impact mission, recent mission, that slammed a projectile into the comet Tempel 1 and studied the material expelled in order to analyze the composition of the comet. So it used, basically photographic evidence, looking at the spectrum of the material that was expelled, bouncing lasers off that material, and really getting a good idea of what that comet was made of by shooting it and breaking a little piece of it off. Okay, and you can see here that, look, this is a comet, by the way. You might be like, wait, are we talking about asteroids or comets? Because this is a comet. The Deep Impact took where the experiment took place was further enough out from the sun that this comet had not developed a tail yet. Okay, and that was desirable for the particular science that they wanted to do in this mission. So they made sure that Deep Impact rendezvoused with the comet further out from the solar system, basically outside of the frost line, so outside of Jupiter's orbit, or kind of somewhere close to or beyond Jupiter's orbit, to get a comet that has not yet formed the tail. Okay, so most comets that enter the inner solar system reside in the Kuiper belt originally. Okay, outside the orbit of Neptune. So any orbit outside of Neptune is considered the Kuiper belt. Okay, just like there's the asteroid belt, now there's the Kuiper belt. We don't call it the comet belt. That might be a good name for it, but instead we call it the Kuiper belt, named after a person. Okay, so occasionally a comet from the far larger Oort cloud wanders into the inner solar system. So if we kind of take that into perspective, we have the Oort cloud is massive and much further out. It is massive, because look at the Kuiper belt. The Kuiper belt already dwarfs the rest of the solar system. The inner solar system, which would be the orbits of Mercury, Venus, Earth, and Mars, don't even show up on the scale of the Kuiper belt. Okay, but then if we take this Kuiper belt and we see its size relative to the Oort cloud, we can see the Oort cloud is so far out. Okay, we have no direct evidence of the Oort cloud. We can't see it with either ground-based or space-based telescopes, and our furthest traveling probes are only somewhere in the Kuiper belt right now. There's a few space probes that are on their way out, like Far Horizons, right, that are on their way out from the solar system, never to return, but they're still within the Kuiper belt. None of them have made it as far as the Oort cloud, nor will they in any century nearby, because it takes a long time to get that far out. We're talking 10, 20, 30, 50 times further than the edge of the Kuiper Belt to get to the Oort cloud. But it is hypothesized, it's theorized that the Oort cloud exists because there's comets that come from some origin, and they seem to come from our solar system, but they're coming from a much more distant location. And to make it clear, when we say most comets come from the Kuiper Belt, that's not because most comets are in the Kuiper Belt. That's just because most observable comets come from the Kuiper Belt. There are more comets in the Oort cloud by a factor of about 1,000. There's about 100 million comets existing in the Oort cloud, but most of them stay there, basically at the very edge of the gravitational influence from the sun. In fact, they're so far from the sun, and the gravitational tug from the sun is so remote for these comets that have these incredibly long orbits that would take millions of years to complete an orbit, that sometimes what pushes them out of their orbit sends them spiraling on a different eccentric orbit that maybe will bring them into the inner solar system. You know what does that? A push from another star, a star that's a couple light years away, right? But since the force is so small here that the tiny little force from another star is enough to push that Oort cloud comet out of its orbit. Okay, so now back to something other than distant comets. Let's just talk a bit more about the Kuiper Belt, which falls under the classification of Beyond Neptune. Well, good place to go when we're talking about the Kuiper Belt, good thing to think about is Pluto. Pluto was discovered in 1930, all right, and it was thought to be needed to explain irregularities in the orbit of Uranus and Neptune. All right, so it was suspected for a while, and then it was confirmed to exist. Okay, so we knew that Pluto was out there. That was pretty cool. All right. But it did turn out in the end that there was no such irregularities, but nevertheless, we did discover Pluto, so some good came out of that study. And that continues today. There's actually further irregularities in dwarf planets like Pluto, and we're studying those because we think there might be another planet, an actual ninth planet that's way out past Pluto. But again, it turns out that we might be wrong because these are such tiny measurements, they have to be very careful how they're made. Okay, so here's Pluto's orbit. It's eccentric and inclined to the plane of the ecliptic. It crosses the orbit of Neptune. So sometimes Pluto is actually closer to the sun than Neptune is, as we can see here in 1989, for example. Right? It's a very, very long orbit. That's why you have to compare between mini Earth years to capture the motions of Neptune and orbit, or Neptune and Pluto. Okay, because you can see Neptune is shown, as is Pluto. But overall, Pluto is further from Neptune. Pluto gets quite a distance away, a significant change here. And if you've seen those recent beautiful pictures of Pluto, that's actually part of the, Pluto has a weak atmosphere, and the atmosphere basically freezes over when Pluto is furthest from the sun at its, basically its apogee, it's furthest away. And then when it's closer in, then that's when the planet becomes more active and the gases start moving around in that atmosphere. Okay, so Pluto's large moon, Charon, was discovered in 1870 or 1978, and certainly not in 1878. It is orbitally locked to Pluto, and it is about a sixth as large. All right, and when we say that they're orbitally locked, it means that the actual center of mass of the two-body system of Pluto and Charon is not within Pluto. So it's more accurate to say that Charon doesn't orbit Pluto. Instead, you can say that Charon and Pluto orbit a point between the two of them that's just closer to Pluto. Kind of neat, right? All right. So there are smaller moons that Pluto has as well, Nix and Hydra. All right. And there are actually even more small moons. So there's just, because again, it seems strange for such a small body to be able to capture moons, but it really might be a testament to the lower energy state of the distant solar system, where there's not as many opportunities for those moons to get pulled and pushed away from other nearby orbiting effects and gravitational effects. So getting caught by Pluto means that small body of the outer solar system is now caught. It was a comet, and now it's part of the Pluto system. Okay, so observations of the eclipses of Pluto and Charon allowed measurements of the orbital details, right? So we're really able to analyze the details by looking at this data taken from these different pictures of their orbits. Okay, and the Kuiper Belt is outside the orbit of Pluto. And sometimes you do hear Pluto as referred to as a Kuiper Belt object, but other times Pluto has a special designation as being a dwarf planet that is near the Kuiper Belt. Okay. It has many, many icy chunks, in other words, comets, and also other dwarf planets. So the current theory is that Pluto is the nearest and largest of these objects, but it's the same type of object. as these other Kuiper Belt objects. Okay? So no objects have ever been observed in the Oort cloud, as I said before. It is simply too far away. That's obviously a goal of astronomy, to get direct observation of the Oort cloud, but we're not there yet. However, some Kuiper Belt objects have been directly observed. All right. So over 1,600 so far. So here we have Pholus in the top, Eris with its small moon. All right. And then we also have Dysnomia in the bottom. Right. Right. So Eris, Dysnomia. Right, so we can see these are different objects. Many of them are Pluto-sized. There's another one known as Makemake, which is about the size of Pluto. All right, so here are comparisons of, here's Makemake, by the way, comparisons of several trans-Neptunian objects with Earth and its moon. So trans-Neptunian just means out further away from the sun than Neptune, okay? So we can see Pluto is quite large. Eris is actually slightly larger than Pluto, but less massive, all right? And then we have Makemake, we have Haumea, right? And then some other ones that aren't as well known, like Orcus, okay? But the point being that we can see that Pluto really isn't that special. It is just one of a classification of these other dwarf planets, these other essentially large comets that are large enough to be spherical, that exist in the Kuiper Belt in the trans-Neptunian region of the solar system. And that's why Pluto was demoted from planet to dwarf planet, because otherwise something like Eris would certainly also have to be a planet. And we didn't want to have more planets because that opens up kind of a slippery slope of being, what do we consider a planet? So instead we say, okay, Pluto doesn't meet the guideline. It's just too small, okay? So in 2006, here's the story of its demotion. The International Astronomical Union, the IAU, adopted an official definition of planet. There had not been one, right? Because it just, we kind of all just agreed on what planets were. And a planet must orbit the sun. It must be massive enough that its gravity keeps it spherical, and Pluto definitely passes that test. But then it must also clear its orbit of debris, okay? And that's the key thing that Pluto doesn't have. There's other debris within its orbit, right? So it wasn't massive enough to pull in those other chunks of matter within its own orbit. And so that's how scientists were able to come up with the test that Pluto did not pass. Okay, and that would also apply earlier when we were talking about Ceres, the only dwarf planet in the asteroid belt. Same thing there. Ceres has other asteroids within its orbit or in its orbit, and so it also did not clear its orbit of debris. Okay, and neither did Makemake, neither did Eris. None of them passed that test. Okay, so a bit about meteorites to wrap up this lecture. So on an average dark night, you can see a few meteors every hour. Okay, so if it's dark enough that there's not much light pollution, you can clearly see those shooting stars, as they're known. The flash is caused by heating. Most meteors do not survive to reach the ground. You're essentially seeing them vaporize. They're burning up as they come into the atmosphere. Right, that's the streak in the flash of light. All right. Meteoroids are defined as being less than 100 meters in diameter. So anything less than 100 meters is considered a meteoroid or meteoroid. Okay. And notice the difference here between, we're talking about meteors and meteoroids, okay? So meteors is the event you see in the sky. A meteoroid is an actual object in space, okay? So most of the smaller ones are the remnants of comets, all right? So a lot of icy pieces to them. Because again, I think I mentioned there's a big distinguishing characteristic between comets and asteroids. I want to come back to that real fast. That comets are icy, all right, and asteroids are rocky. Okay. But anyway, so the example of a comet that's broken up would give us those small chunks that are 100 meters or less. If the Earth's orbit intersects a comet, meteor showers occur. Because essentially what happens is the comet is going to leave these trails of debris, and then Earth passes through those debris trails. That's why you often hear about, oh, it's the time of the year for such and such, meteor shower. Or the Gemini meteor showers coming up. There's all these named meteor showers throughout the year. Perhaps you've seen a little news story about, tomorrow night's going to be a meteor shower. And those are always seasonal events. And the exact day of the year changes a little bit. And the reason that they are these calendar events is because Earth is going to keep passing through this leftover trail of debris every year. All right. Now, eventually that trail of debris will disperse and there's not going to be anything left to pass through. But for many years, Earth's going to pass that trail of debris left over from a comet, and that's going to make a yearly meteor shower. And there are many of those, right? There are many of these little chunks of debris that Earth passes through in its orbit, which is pretty neat. Okay. And so that's a meteor shower as compared to just random meteor events, which are continuous throughout the year. And meteor showers, it can be a whole bunch at once. The sky can be, practically full of them, just one after another. Okay. All right. And then, and as I said before, and that will continue to happen until all the meteoroids have burned out. Okay. So here are the major meteor showers that are currently happening on dates like, January 3rd, right? We got the Perseids on August 11th, the Orinids on October 20th, and these names, the Lyrid, the Perseids, these are named after the constellation in the sky visible on that night of the year where the comets are most visible. They're usually visible throughout the sky, but there'll be one pocket of the sky where they're most visible, and that's often where the name comes from, right? So the light, like for example, the Lyra constellation is where the best place to look for the Lyrid meteor shower on April 21st. Okay, which just recently happened. All right. So larger meteoroids are usually loners from the asteroid belt. They're much rarer, and they've produced most of the visible craters in the solar system. So all the craters that we see on the Moon and Mercury, those came from meteoroids that were kind of not part of a comet trail, but are these actual big asteroids from the asteroid belt. The Earth has about 100 such craters that are more than a tenth of a kilometer in diameter. Erosion has made most of them hard to discern. Often you need to see them from an aerial photo. You wouldn't recognize them on the ground. One of the largest ones is actually in Canada. You can see an example of it there, where it's been filled in by lakes. All right. And meteoroids that burn up in the Earth's atmosphere have densities between 500 and 1,000. So a density less than about half water here is half the density of water. And then 1,000 is the density of water, 1,000 kilograms per cubic meter, that is. Okay, and so they're probably comet-like, right? So mostly composed of lighter material ices. Okay, H2O ice, also methane ice, ammonia ice, and such. Okay. On the other hand, meteoroids that reach the surface have densities of about 5,000 times that, or five times that of water, which is 5,000 kilograms per cubic meter, and these are similar to asteroids, right? They're rocky. Okay, they're going to be probably silica type. There's probably some carbonaceous types ones as well. Okay, and also the rare nickel or iron type asteroid. Okay, here are some examples of some large asteroids that have embedded in the Earth, right? Earth's core. Now meteorites, right? Because in a meteor is what you see in the sky. A meteoroid is just a small object in space that's either icy or rocky that's less than 100 meters in size. A meteorite is a meteoroid that passed through Earth's atmosphere, appeared as a meteor in the sky, but didn't burn up, because a meteorite is the actual surviving rock. Okay? And that's why it has the ITE sound at the end, because it's like a rock, meteorite. Okay? So it's rocky, right? Some are more metallic, right? So they don't have to be rocky, but the point is that there's a surviving chunk. You're never going to find a meteorite that's icy, because even if it didn't burn up in the atmosphere, it'd melt, even if there was a chunk of ice that made it to the ground. Okay? All right, so here's an example of rocky and metallic meteorites. Okay, so now let's summarize the debris of the solar system. Okay, so most asteroids orbit in the asteroid belt. Okay, the asteroid belt is closely connected to Jupiter, both in maintaining the asteroid belt through gravitational resonance and in creating the Trojan asteroids due to gravitational balancing effects known as the Lagrange points. Okay, but so Jupiter is very important in the context of the asteroid belt. All right, the total mass of all the asteroids is less than the mass of Earth's moon. So if you total them all up, they're not a significant portion of the solar system, but they do continue to affect the solar system, so we care about them certainly, but their mass is not that large. They do come in three types: the S-type silicate, N-type metallic, and C-type carbonaceous. A few asteroids are Earth-crossing orbits, and we monitor those. On the other hand, comets are icy and normally orbit far from the sun, right? Most of the ones that we track coming from the Kuiper belt. Some comets have highly eccentric orbits and enter the inner solar system. Other ones always stay out of the inner solar system. In fact, most do. The vast majority of comets reside in the Oort cloud and stay there all the time, right? For hundreds of millions and billions of years. The Kuiper belt is just beyond the orbit of Neptune. A number of Kuiper belt objects have recently been observed, right? That's definitely an ongoing part of astronomy, finding new Kuiper belt objects. So many fascinating discoveries that you made out there. Comets that do come into the inner solar system begin to vaporize. as they approach the sun. That vaporization is going to create the tail. It's also going to create a coma, all right? And the tail of an asteroid can be enormous, covering 30 or 40 degrees of the visible sky, right? So, they have this huge tail because that tail is 20, 30 million kilometers long, okay? Meteors are bright flashes of light from the micrometeoroids hitting the atmosphere. If a meteor lands on Earth, it is called a meteorite. Meteors that burn up in the atmosphere are mostly similar to comets, so mostly icy. Those that land are more like asteroids, right? Good rule of thumb there. The gradual disintegration of a comet as it orbits the sun leaves a meteoroid swarm. And if Earth encounters a swarm, we see a meteor shower. See how all these terms come together? Kind of neat there. All right. Well, that concludes lecture 14. Thank you so much for watching. I hope it has been interesting and informative.